Chris Long, Dominic, this is cluster 3 of Cosmos 2014, IT Davis. So my topic is low speed aerodynamics. So as you guys know, the main forces on the airplane is lift, drag, thrust, and weight. And so since it's aerodynamics, I'm just going to focus on lift and drag, and that's just an air vortex when a plane takes off. So in important terms, laminar boundary layers is a smooth flow of air over the top of the wing. Because of air friction, this usually turns into a turbulent boundary layer right here. And then generally the flow separates later, creates like unordered flow, high pressure, which leads to less lift. Aspect ratio is span squared over the area of the wing, and the Reynolds number is, as you guys know, is the ratio between normal pressures on the wing and shear stresses, which is like air friction on the wing. So friction and lift and drag have to do with laminar flow and separation point. And so in this picture you have an angled flat plate, and the flow separates and reattaches at the leading edge, and then the flow flows smoothly off the end. So this causes a bigger boundary layer on the top of the wing and higher pressure on the bottom of the wing, and it creates lift. If the angle of attack is too high, then you have leading edge separation, a lot of it, and so that creates less lift. Here and here, usually planes nowadays have curved airfoils and thicker airfoils, which leads to better performance over a range of angles. But still, if your angle of attack is too high, you get trailing edge separation here. It causes unordered flow, high pressure, and less lift and more drag. So that's why most planes have this. Angle of attack and lift coefficient, as you can see, it's like literally related until a certain point. This is where the critical angle of attack, which for most airfoils is like 10 to 16 degrees normally. So that's when the lift coefficient goes down. In general, lift coefficient, it's lift over half of rho squared S. S is the area of the plane wing. And so when you have too high angle attack, you start to stall. That's when you get your flow separated, and then you get a lot of drag. Okay, so increasing lift, flaps increase the torque on the airfoil. And so this increases the coefficient of lift max. However, it decreases your critical angle of attack, so you don't want to use it for too long. So it's only used for takeoff and landing. Leading edge devices, you have these two fixed slot and extendable slats. The gap in the middle lets flow from the bottom go to the top, which delays separation and increases your lift. Kruger flaps, they increase the camber of the airfoil, which leads to more lift. Drag overview, most drag is you can induce drag, and flat plate friction, which is just skin friction drag. Induced drag is caused by difference in pressures, and skin friction is due to surface roughness. So here's surface roughness, as you can see, close up picture. Air molecules hitting the surface of the wing and slowing down. It creates this turbulent boundary layer where the air close to the wing is really slow, and then air away from the wing is faster. So roughness causes separation of flow. Induced drag, so lift creates drag, we talked about this before, so a component of the lift causes drag. So in general, the coefficient of induced drag is about coefficient of lift squared over pi a. A is the aspect ratio. So this is, okay, so the optimum coefficient of induced drag is given by this integral. You're just adding components of the coefficient of lift over the area of the wing. And so for an untwisted elliptical wing, the alpha angle of attack and coefficient of lift is constant. So if you solve this integral, you get this. And so adding another equation for angle of attack, you get coefficient of lift squared over pi a. This is like the optimum coefficient of induced drag you can have, and that's for elliptical wings. Most notable example of that is like this plane is called the Spitfire, used in World War II. And then for other plane shapes, this expression for coefficient of induced drag is very similar. It's basically this form, adding a small number. So next one's on the form drag in a second. So here this is an extreme case. So you have a flat plate normal to the airflow. And so in this case, the airflow separates right when it gets to the top. You get a big area of high pressure and unordered flow. And so it creates a lot of drag from pressure imbalance on both sides of the wings. For circular airfoils at low Reynolds numbers, the flow separates right over the top, creating this big area of high pressure. Again, leads to form drag. High Reynolds numbers, the separation is delayed. So there's less form drag. You get the smaller area of high pressure, but you still get some form drag. This happens on like most of airfoils to some extent. So yeah, usually you want like a higher Reynolds number to decrease form drag. So in summary, the Boeing 747 it uses Kruger flaps in the front to increase camber, multi-slide trailing edge flaps in the back to increase lift, and this leads to it can slide more than 800,000 pounds of lift when it's taking off. So Fourier, so his main discovery is approximating functions with sines and cosines. Here, this black line is a square wave function, and the blue line uses 21 terms of sines and cosines. As you can see, it's a pretty good approximation, while if you just use 1, 3, and 5 terms, it's more rough. For periodic signals, it's just using different amplitudes and frequencies of cosines and sines. Using Euler's formula, you get this summation of exponentials, and x of n is just coefficients. Given my integral T naught is like the period of the periodic signal. He extends this to non-periodic signals by thinking of them as signals with infinite period. For inverse Fourier transform is just another name for the approximation of the non-periodic signal. Fourier transform is the coefficients of this approximation. And so this is cool because Fourier transform takes the signal and puts it into the frequency domain by giving coefficients of the exponentials for each frequency as part of the signal. We'll see that in just a second. A pretty simple example. So this is function sine x plus sine 2x. Here's part of the frequency domain. And then as you can see, there's only 2 non-zero values, which means that there are only 2 frequencies represented in this signal, which is obviously true because it's only sine x plus sine 2x. For coefficients, they're generally complex numbers. The length of this complex number is called the Fourier magnitude. And in application, this is the easiest thing to measure from a signal. And we'll see that in just a second. But yeah, the Fourier magnitude is just the length of this complex number. These plots the Fourier magnitudes when you say heat or hit or head, or whatever these words are. The tips of these are called formants, and that's actually how your ear detects what word has been said, and these shapes are just how your mouth looks like when you're saying the word. Obviously, in reality, your voice is a lot more complicated, a lot more frequencies, 4,000 frequencies here, and here are the magnitudes, so it just shows that it's really complicated in real life, and then you only want to measure the Fourier magnitudes because that's the easiest. Fourier also did the heat transfer equation. Q is the density of the local heat flux. K is thermal conductivity constant, and change of T is the change of temperature. For one-dimensional heat transfer, we have the heat flow rate as proportional to the area of the cross-section, and the change in temperature over the change in length. So the most simple example of this is just a wire here of heat transfer through wires. This one, that's like constant density probably. So yeah, Fourier came up with this. So Joule, he did research on electricity, heat, and magnetism. He was an English physicist. Most notable achievements was disproving the caloric theory and its influence on thermodynamics, specifically the first law of thermodynamics. So this is his first law. So this experiment, he ran current through a wire, and this wire went to a tub of water here. And so you measured the raise in temperature. He found that the heat dissipated from the wire is proportional to the I squared R, which is current, and resistivity. This disproved the caloric theory, which at the time was it was really that heat was this fluid called caloric that moved from one body to another. And then so this was the first law of thermodynamics, which is that energy can be changed from one form to another. Obviously, that kind of shows because electrical energy went to heat. So another experiment with heat, he dropped a known mass from a known height. This turned paddles in a calorimeter of water, and he measured the raise in temperature. And through this, he discovered the mechanical equivalent of heat, or foot-pounds per British thermal unit. And so this again proves his first law of thermodynamics because potential energy is going to kinetic energy, which is going to heat. And so this also disproves caloric theory because the heat just seemed like it seems like it came out of nowhere. Magnetic restriction. So Fourier discovered that in magnetic fields actually changes the shape of the magnetic dipoles in a metal, and actually changes the dimensions of the metal slightly. And so this is an exchange between magnetic and mechanical energy, another way to prove first law of thermodynamics. Terminal D is just an alloy that we'll talk about later. It's used in application for this discovery, magnetic restriction. So yeah, as you can see, the magnetic dipoles change, and then the metal changes dimensions. So this is most commonly used in sensors and actuators. So these small elongations are used to control small pumps or motors in the hydraulic system, whatever. And then terminal D is just the most magnetic of all alloys, so it's the most easiest to change dimensions. So that's why it's used in application. So here's a simple diagram where you have electric current, and you have a wire. You control the current in the wire, thus controlling the magnetic field, thus controlling how much your metal changes shape. So Biggest impacts of Fourier can be postulated functions with sines and cosines, and Joule found the mechanical equivalent of heat and really lets the first law of thermodynamics.